So, in the last few lectures we have been talking about the clocking and the various timing issues that may arise in a design, and what are some of the constraints like hold time, skew, setup time, etc. They have to be incorporated to have a correct operational system. Today in this week, actually we shall be starting our discussion on something called timing closure. Timing closure means, you see, we may be having some requirements which may come from the specifications, that what we really want, what kind of timing behavior is desired or is required from the circuit that we are designing. But it is possible that when you have designed the netlist, when you have placed, routed the blocks, the interconnections, the nets, then it may so happen that some of those timing constraints might get violated. Timing closure broadly says that how to evaluate, well, in a fast way, whether any of the constraints are getting violated, and if we see any violation, what are the measures we can possibly take or adapt so as those violations can be avoided, right. So, this is the topic of our discussion next week, timing closure. So, you see, so when the layout of a chip is created, so when I say layout of the chip is created, it is through the entire back end design process. So, from the netlist that we get from the front end design, we can do some circuit partitioning, then we can do possibly floor planning and placement, routing, and then the final layout, right. This is what the final layout of the chip will look like, and the layout must satisfy two constraints. See, the first is called geometric constraints. These are something which we shall be discussing in some detail later. Geometric constraint says that the cells obviously have to be non-overlapping, and there has to be sufficient space in between for routability. Like when we say geometric constraints, it is not just the cells or the blocks, it is means even it can go down to the lowest level when we consider the final layout of the chip. Now, in the final layout of the chip, we have the different layers, as I mentioned, if you recall. So, there the basic features will look like rectangular regions, and those regions may exist in the polysilicon layer, diffusion layer, metal, various layers of metal, and so on. So, finally, we have some rectangular regions. So, some of the constraints that may arise at this layer may be like, let us say I have two lines, maybe this may represent interconnections running parallel to each other. There are two things. What is the width of these lines? Because width of these lines will determine what will be the resistance of these lines, R1 and R2, right. Secondly, the separation between these two lines. The separation of these two lines will determine the capacitance between these two running wires. So, basically, as I mentioned earlier, that when you have a long transmission link, the RC delay comes into the picture, and there are some approximate ways to model these delays, like the Elmore delay model. So, similarly, here also when some wires are laid out, there can be some RC delays, and these delays will be dependent upon the width of the wires, of course, the lengths. So, what will be the length of the wires, and the separation from some other parallel wire, that will determine the entire wire capacitance, right. Fine. So, this will be the first kind of constraint, the geometric constraint, and the second kind of constraint we have already talked about earlier, that when you have the storage cells in a system, the flip flops or the latches. So, these storage elements will have some inherent setup and hold requirements. So, you recall what was the setup time? So, whenever a clock edge comes, how much before that I must make my input stable, that is the setup time, and the hold time says after the clock edge how much more time I should keep my data stable, otherwise the flip flop may behave incorrectly, right. So, this setup and hold times, these are characteristics of the storage elements, and these are some things which are not under the designer's control. Designer can control a clock skew by different layout of the clock tree, for example, right. So, the other timings you can control, but this setup and hold times are something that are characteristic of the storage devices that we use in a design. Okay. So, the overall optimization process that targets to meet these requirements is broadly referred to as timing closure. Now, here we shall also see later that timing closure does not only look at a netlist and tells you whether the geometric and timing constraints are being met. Well, you can also have timing aware placement and routing solutions, so that you create a placement, you create a routing such that your final timing constraints or targets are achieved. That is the modern, you can say, modern day design flow for back end design of a high performance chip or circuit. Okay. So, talking about timing closure, as I said, placement and routing forms the important parts. Now, broadly there are three things here. First is of course the placement. So, how to place the blocks such that the signal delays will meet the timing constraints as per our requirements. Now, you see, once the block placement is finalized, then only we can make some realistic and means accurate estimate of the you can say the delay estimate, like the interconnection delays, the gate delays or the cell delays and so on. But once the positions are not fixed, these delays can also vary, and just now as I said that the delay is just not a function of how long the wire is, but also on the neighborhood. What are the other wires which are running in parallel, maybe on the same layer or on different layers? There will be capacitive effect, there will be something like crosstalk, which also we shall be discussing later. So, all these things also have to be taken care of, right. So, this is placement. Then we have timing driven or timing aware routing. So, again, so how to lay out the different nets using metal connections typically, so that the signal delays conform to our constraints or requirements, right. And what might happen is that after this placement and routing, we may find that some of the delays are still not meeting our requirements. So, then we may have to revert to something called physical synthesis. So, here what we do, we apply a variety of techniques. So, this we shall be discussing some of this later in more detail. These techniques are used to reduce the delay of a particular net. So, what are the broad approaches? There are several others also, the main approaches are mentioned here. So, you can make a transistor or a gate bigger or smaller, this is called sizing. So, if you make it bigger, the delay will decrease, if you make it smaller, the delay will increase. So, depending on whether you want to decrease or increase the delay of a path, you may properly size a gate or a transistor. This is the first technique, and the second one we talked about when we discussed the clock net design, that whenever we have a long wire, the propagation delay may be higher. So, it is always good to insert buffers in between, so as to decrease the overall propagation delay. And thirdly, we may have to restructure a circuit along the critical path. This also we shall be discussing later how we can do it. But broadly, these all are techniques using which we can reduce the delay of a circuit. Okay. So, what is the main motivation behind this step of timing closure? Because you see, in the earlier days of design, we did not worry about timing that much. We were more concerned about the functional correctness of the circuit, whether the circuit is working correctly or not, and main, you can say, component where the most significant amount of delay took place. During that period, we often ignored the interconnection delay. So, what we are saying is that signal propagation delay was the main contributor to the overall circuit delay, and during those period we had ignored the delay of the interconnection wires. Because of this, cell placement and routing did not affect circuit performance, because when we evaluated circuit performance, we only talked about the delay of the gates, we did not talk about the delay of the interconnection. So, it is immaterial whether the wires are short or wires are longer, we assumed that interconnection delays were negligible as compared to the gate delay. But subsequent to 1990s, when the devices started to scale down, the MOS transistors, this is called technology scaling. So, here the situation started to change. So, the relative impact of the interconnection delays started to increase, and today we have a situation where the interconnection delay is becoming predominant as compared to the gate or cell delays. So, the next slide will give you an idea. Look at this first diagram, just two gates, the output of one gate is driving another gate. So, what we are evaluating? We are trying to evaluate that we are applying some input to the first gate. After some time, after how much time, the corresponding values are coming to the input of the second gate, this total delay, right. Now, in the 80s, the scenario was that most of the input to output delay, this total delay, the contributor was the logic gate. Roughly, this 85% of the delay was contributed here, and the rest 15% of the delay was contributed in the interconnections. But in the mid 90s, the interconnection delays, well, they started to go up because the wires become thinner, and also the gates became smaller, they become faster. So, now the contribution becomes roughly 50-50, 50% here and 50% there. So, half of the input to output delay of the logic will be due to the interconnections and half due to the gate delay. But you see, today when you are into the deep submicron technology domain, here the situation has reversed. Now, in the interconnections we are expecting about 80% delay or even more, and while the gate delay is only 20%. So, as you can see, today in the high performance circuit design or the physical design, modeling of the interconnection and properly routing the interconnections, this has become most important, this is of paramount importance, right. So, this is what this scenario is today. Now, let us have a quick recap of the setup and hold times, because we shall be using some of the delay related assumptions in our subsequent discussions. So, what we discussed when we discussed the clocking, there we said that when we consider propagation delays through circuit components, like when we say propagation delay through circuit components, we are saying that there are some storage elements. Let us say I have a set of flip flops, register R1. So, I have another set of flip flops, register R2, and there is a combinational circuit in between. So, there is a clock which is feeding both these registers. So, what we said is that the clock will be having certain time period, let us say like this. The clock will come, this is the clock period, let us say capital T. Now, what I am saying is that on which means on what factor will this time T depend? Well, of course, it will depend on the delay of this combinational block, let us call it delta. So, it will depend on delta. This will also depend on setup time. This will also depend on hold time, because see this combinational circuit will be taking some time to compute, and after that this data will be available at the input of R2, so that I can apply the clock. But the setup constraint says that before the next clock edge comes, so I must be giving some minimum time before which the input must be stable. So, not only this delta, I must add the setup time to this total capital T, and this hold requirement says not only that, even after the clock edge comes, I must maintain the input stable for some more time after that. So, my total clock period should include not only delta, but also the setup and hold times. In this way, my total clock period will go up, right. This was the requirement. So, the timing optimization tools that we use, they try to adjust the propagation delays to satisfy these two constraints. Now, you see setup constraint is sometimes called long path constraint. What it says, just to recall again, this is the time the data input must be stable before the clock edge with respect to every storage element or register. So, why do we call it a long path constraint? Because you see, so here we are saying in the with respect diagram that there must be a minimum time here before which the data must be stable. So, there must be a maximum worst case propagation delay of the combinational circuit. That is why I am calling it the longest path, because in a combinational circuit some paths may be short, like for example, I may be having a circuit like this, let us say I have a circuit like this. There are two outputs. The first output is generated only after a delay of a single gate, but the second output is generated after a delay corresponding to 3 gates. So, here when I say the longest path, it will be the delay of the second output equivalent to 3 gate delays. So, I must take that into account. So, what is the maximum value of delta? So, what is the value of delta after which the outputs will definitely be stable, because this will become stable much earlier, just after a 1 gate delay. So, that delta must include the longest path, right. So, whenever we are considering the setup time, okay, that is it. And hold time constraint, why it comes in? So, hold time is the time we must keep the data stable after the clock edge. This tells you that even after the clock edge, I must keep the data stable for some time. Why? Because if the input data changes before that, maybe the second register will be accepting the previous this new changed data in that same clock cycle instead of going into the next clock cycle, because registers will take some time to respond to the clock edge. So, whenever a clock edge comes, register does not respond instantaneously, it will take some time. So, it is said that there must be a minimum time out here, this time, this is the whole time. You must keep the data stable so that this register can faithfully record and store the input data. If the input starts changing in the meantime, then there can be wrong data getting in. This is a short path constraint, it is called, because the short paths can create a problem here. So, you will have to consider two cases, delta max and delta min. So, when you talk about the setup time, you need to consider delta max. So, what is the maximum time that may be required for the output to become stable, and after that you have to give a time of t setup. And t hold says that not only that, the minimum time of this delta, because within that same clock cycle this register 2 times, therefore I have to have this kind of a tolerance. Okay. So that's why this is called long path and short path constraints, this setup and hold constraints. Okay. So just to refresh whatever I have said, in the setup constraint we ensure that no signal transitions occur too late, and the constraints are the total cycle time or the time period must be greater than or equal to the combination circuit delay, the setup time, and of course the clock skew if any. So the initial phases of timing closure normally focuses on the setup constraints. So what it does is that it checks whether a circuit meets the setup constraints. So what do I need to do this? We need to estimate the combinational delay, T comb delay, right, because setup and skew are already known, I am assuming. So this is a process we need to carry out. So how long signal transitions will take to propagate across the combinational circuit, means from one storage element to the next. So the registers are placed in stages and there are combinational circuits in between. We need to have a good estimate as to what is the estimate means the delay of the combinational circuit. So from the output of a storage element, how much time you can take for a signal transition to reach the input of the next storage element, and this process is carried out through a technique which is called static timing analysis. So we shall be discussing this in more detail later. So static timing analysis, essentially it does two things. It starts with a given netlist of a gates or transistors, so a given circuit netlist, and it tries to calculate the actual arrival times of the signals and the required arrival times. We shall be going into the detail of this later. Required arrival times may be provided by the user with respect to the output. So you have to calculate them for every terminal or every gate. Now once you do this, so you can identify something called slack, which is the difference between RAT and AAT, and that can identify the timing violations. For some cell you may find that the actual arrival time is becoming greater than the required arrival time. So there is a timing violation there. So you may have to adjust the timing in some way so that those timing violations are addressed, right. So this we will see, and for static timing analysis normally we model the signal transitions, the delays, as the worst case values, and we shall also see there is something called false paths which are also considered. False paths are like this. You see, I have a combination circuit, so I am saying that for estimating the minimum clock period required or the maximum clock frequency, I will have to estimate the worst case delay. Okay. This I normally do using static timing analysis. Now what I am saying is that the longest path in the combinational circuit need not necessarily mean the longest delay, because there may be a path, but the circuit may be such that no signal will follow through that path. We shall again see some examples later. These paths are called false paths. There are paths which are geometrically you can see there is a path, but with respect to the signal value, the gates will work in such a way that signal will never propagate along those long paths. So if you can identify the false paths a priori and remove them from your consideration, then your analysis can become much faster. This is one important point. Okay. So, as I said, once you have calculated the required arrival time and the actual arrival times, for every point x in the circuit, this may denote the input to a gate, output of a gate, some pins. You can calculate the slack. So, a positive slack means your required arrival time is greater than the actual time, actual arrival, which means your timing violation is not there. But if RAT is smaller, that means this is negative, which means there is a timing violation. Now, if there is a timing violation, then we have to go for physical synthesis restructuring, where we modify the netlist so that the actual arrival time can be reduced, so that the slack value can be again made 0 or positive. Okay. Now, there are a few ways in which you can do that. I will just explain a few of them. The first technique what is mentioned here is that gates lying on the critical path can be upsized to propagate signals faster. So, what I mean is something like this. Let us say there is a gate here, say an inverter, there is another gate here. Suppose this is the path which is creating the problem, for which the slack value is negative, right. So, we are trying to reduce the delay of this path. So, how we can do this? Let us see. This inverter, if you look at the CMOS level realization of an inverter, just this is a PMOS transistor, this is an NMOS. So, the input is coming here, the output is going from here, and similarly this side you have another such. So, your circuit is like this. Maybe this is driving some other gate, right, some other gate it is driving. So, it will be driving something else. So, the way we model this is that, you see, this is an interconnection line, there will be some parallel lines here, there will be capacitances, there will also be gate capacitance, because it is ultimately driving the gate. So, if you think about the gate of a MOS transistor, there is a that looks like a parallel plate capacitor, gate on top and the substrate at bottom, and substrate is normally grounded. So, essentially what you can model is that as if this is driving a capacitor, a capacitive load. Similarly, when I say this fellow is driving some other gate, so here also there will be some capacitive load, let us call it C1, right. So, when I say that the signal at the output of a gate is going from 0 to 1, let us say, what does this mean? This means the capacitor is charging from 0 to high voltage via this path. So, this p type transistor is coming into the picture, and similarly when I say that the output of this gate is going from 1 to 0, which means the capacitor was already in the charge state, it is 1 high, it is discharging through this path. So, now the discharging path will be like this. So, either the PMOS transistor or the NMOS transistor will be conducting. So, if I just assume for the sake of argument the resistance of these two transistors when in the conducting state they are equal. So, the charge discharging delay will be RC, product of that. Now, in this method what we say that we are scaling up a transistor. Scaling up means, let us say earlier my channel or the gate which was above the channel was like this, this is one terminal, this is one terminal. Now, what I make it wider, say by 2 times. So, if I make it wider, what will happen? If the resistance of this was R, this resistance will become R by 2, right. So, if I scale up the transistor, make them bigger, let us say R by 2, then my delay will become RC by 2, right. Similarly, if I want to increase the delay, I can make it narrower, I can make it 2R. So, just by scaling the transistor, we can have a very nice way of controlling the delays of the different segments of the wires, right. This is exactly what we mean by the first point. Gates lying on the critical paths can be upsized to propagate signal faster. The second point I talked about while discussing clocks, let me again look at it once more. Buffers may be inserted into long critical wires. Let us say there is a long wire of length n. Now, with respect to the Elmore delay model, if you consider distributed resistances and capacitances, the delay is proportional to the square of the length. So, let us say it is equal to some constant, let us say k into n square. So, what we are saying is that to speed up the circuit, what the proposal is that this was the whole line. Now, you insert some buffers in between. So, break it up into some segments. Let us say there are m segments 1, 2 up to m. So, now delay of every segment will be how much? Total length was n. So, width of each segment will be n divided by m, because there are m such pieces I have made. So, delay of each segment will be k into n by m whole square, and there are m such segments. So, multiplied by m, this will be the delay here. So, if you make a short calculation, this becomes k n square divided by m. So, roughly the delay decreases m times, right. So, you see if you insert buffers in between, this is a nice way to reduce the delay. Of course, the price you are paying is some additional area for the buffers, right. This is of course a trade, a design trade off you are making. You are investing a little bit of hardware to make the circuit faster. And thirdly, of course, the netlist tree you can restructure to decrease the overall depth. This is very simple. I am giving a very simple example. Suppose you have a netlist like this. Just a 4 input NAND function. Let us say if the inputs are A, B, C and D, the output produces is A, B, C, D. So, you can basically restructure it like this. These two are functionally equivalent. So, here the delay was 3, now the delay was 2 levels of gates. So, this kind of restructuring of the netlist is also a very simple way to reduce the delay of a circuit. Now, we shall see other methods also later. So, how we can enhance the delay of a circuit, that we shall be discussing later. And with respect to the hold time constraint, this I mentioned that these are the early signal transitions that create a problem. So, for hold time constraint, this also we discussed earlier, that to address the hold time constraint, that means you are within the permissible limit, you must ensure that your combination circuit delay must always be greater than equal to hold plus skew time, and this combination delay now is the minimum possibility, not the maximum, this is greater than equal to. So, the minimum possible delay must be greater than equal to this time, this must be ensured, right. So, with this we come to the end of this lecture. We just continue with our discussion in the next lecture also. Thank you.